Hello mathematicians, we're now going to have a look at dynamics. So we're starting the Extension 2 course proper now, and the Extension 2 course is more focused on dynamics, which is the study of why objects move. So kinematics was a study of how they move, dynamics is why they move. And the essence of why they move is Newton's second law. So a body is going to change its velocity in either magnitude or direction. That is, it will experience an acceleration if a force is applied. And by Newton's second law, the acceleration is linked to the force by F equals ma, as long as we use SI units. So that's kilograms for mass, meters per second squared for acceleration, and newtons for force. So we've already seen that acceleration is dv dt, or v dot, or x double dot if you like. And dv dt we know we can write by the chain rule as dv dx times dx dt, which gave us another way of writing acceleration as v dv dx. We could also take this expression v dv dx and we could rewrite v as d dv of a half v squared. And the purpose of doing that is that if we then look at our chain rule, these will cancel out, so we get that a is d dx of a half v squared, which gives us the ability to work with expressions for acceleration, which are functions of x. So, in summary, if a is a function of time, then we would generally just use dv dt or d2x dt squared, as we did in the Advanced and Extension 1 courses. A is given as a function of x, we would generally use d dx of a half v squared. And if a is given as a function of v, then we would tend to use dv dt if the initial conditions are in terms of t and v, or we'd use v dv dx, so this bit here, or here, if the initial conditions are in terms of displacement and velocity. So let's have a look at some examples. So we have a particle moving in a straight line, an acceleration which is inversely proportional to t cubed. So that gives us this, that a equals k on t cubed. The particle has a velocity of 3 meters per second when t equals 1, and its velocity approaches a limiting value of 5 meters per second. So we need to spend some time getting what I've called loosely a diagram to describe this. So if the particle is moving along in a straight line, it starts at some initial time, t equals 0, at some time later, so when t equals 1, v equals 3. We could also possibly put in that at some time later, when t equals t, v equals v. But ultimately, it's going to keep going along this straight line, and as t tends to infinity, so that is, its velocity is going to approach a limiting value of 5 meters per second. So we've got a as a function of t, so we can use the fact that a equals dv dt, and then recognise that we rewrite that in terms of integration. V equals the integral of a dt. So the integral of k on t cubed dt, which we can cope with, gives us our constant of integration. We put in our conditions when t equals 1, v equals 3, and we get an expression for c in terms of k. So we haven't yet had anything to help us get rid of k, our constant of proportionality. So the best we can do is rewrite or write our equation for velocity. So that's our c, 3 plus k on 2, and minus k on 2t squared. Now, the thing is that as t tends to infinity, v tends to 5, what that lets us do is to say that almost regardless of the value of, when t tends to infinity, this last term becomes 0, so our expression for velocity above reduces to this. So we then have k equals 4. Once we know that k equals 4, we can put that back up into our expression for velocity up here, and we can then get a velocity equation where v is simply a function of t. And we can just double check that when t does tend to infinity, that term there is going to drop off, it's going to head towards 0, which gives us v equals 5. Now in our next example, the particle again moves in a straight line with a retardation. So we have to know the significance of this in, I guess, physics terms. So it's retarded is the same as that it has a deceleration. So it has a negative acceleration, which means an acceleration acting in the direction opposite to the velocity. And this negative acceleration increases uniformly, so that would be in magnitude, with the distance moved. So the further the particle moves, and I've shown it here moving to the right, the further that particle moves to the right, the bigger the value of the acceleration pointing towards the left. Now this is another good example of why it's necessary to read it carefully and gather all your information together. So in the next couple of lines, we're trying to get a picture of the motion. So initially the retardation is 5, so that means it's got an acceleration of 5 meters per second. Towards the end it says initially the velocity is 20 meters per second, and assume initially its displacement is 0. Sometime down the track the acceleration or the retardation is 11, so the acceleration is minus 11. We don't know its velocity at that time down the track, but we do know that it's 12 meters from the start. And again, somewhere down the track, when we don't know the time, when we don't know the acceleration, it's going to come to a stop, and we want to find that distance the particle moved. So this little summary here, I think, is key to the whole problem. And then going back and finding a starting point. So our starting point is this, that the acceleration is increasing uniformly with distance. So that means that it's a linear function, a equals mx plus b, because it increases uniformly. So then we can start to put in bits and pieces we know. So a equals minus 5 when x equals 0 lets us find a value for b in our linear setup. And then, knowing that when x equals 12, a is minus 11, lets us find a value for m, so we can finally get an equation for acceleration in terms of displacement. Now, because we've got acceleration in terms of displacement, we can then use d dx of a half v squared equals minus a half x minus 5. If I then integrate both sides with respect to x, which is this, then I've got that. The integral of this side will give us our half v squared over here. Stock integral, I get that. I can find my constant of proportionality because when x equals 0, v equals 20, so I can find c. Therefore, I can get my equation for a half v squared. And what I'm interested in is what's the value of x when v equals 0. So when v equals 0, if I try to find my value of x, I'll have a quadratic to solve, which will give me two solutions, negative 40 or 20, and obviously negative 40 doesn't make any sense in this particular problem. So 20 meters is how far it goes to the right. Now this is a question where I've started to think about how it would look if I did it in terms of that extension 2 technique. So when I did my integration here, rather than being an indefinite integral, I could say I'm definitely going from when velocity is 20, so that was initially, till when velocity equals 0. That's the part that I'm interested in. So this becomes a half v squared from 20 to 0. And over that same segment of the journey, my displacement will go from 0 to some value of x, and I'm interested in that value of x. I'm integrating that, so I put my limits in here. When I evaluate my definite integral now. I get minus 200 equals that, which takes me back up to this spot here. So takes me straight to my quadratic to be solved and gives me the same answer. Now, I'm not saying which way you have to do it, and I will switch as I do them as well. But you might like to go and now do set one and mix it up. Mix the techniques. Maybe do this, a question you're comfortable with by both techniques and make a decision.